short as they were before. You best start bracing. Did you think you could keep us out? Shut the gates, forget us now. Tides are changing. Can you hear this sound? Can't stop us now. We're not back in town, know what we're doing. Things are about to change, it's evolution. Voices shake the ground, you feel it moving. We're the revolution. We're the With the ground beneath your feet, with a whisper in the tree. Do you feel us watching? Hunger in our eyes, victories on our minds. It's our time to rise. Can you hear the sound? Can't stop us now. We're not back in town, know what we're doing. Things are about to change, it's evolution. Voices shake the ground, you feel it moving. We're the revolution. We're not back in town, know what we're doing. Things are about to change, it's evolution. Voices shake the ground, you feel it moving. We're the revolution.
So the commotion, get ready for explosion, we rollin'.
Good evening and welcome everybody, this is Obi-Wan Pez for Ensign Pachenko, super late comparatively to when I usually stream, so we'll see how it goes. So, tonight we are going to be doing some calculus out of cracking the GRE math test. It's the subject test from the Princeton Review 2nd edition. Copyright 2002, but that's okay because the test doesn't change that much. Mostly this is going to be, for anybody who doesn't know, a source of problems. So we're trying to get all of the different ideas out onto the internet and say, well, this is what we're really going for, regardless of whether or not it's exactly the same. It's fine. It'll just be something reasonably similar. So what we've got at the moment is that we're going to clear the canvas. Okay. I did want to take one suggestion from from another source, which was we were looking at Okay, so we're going to go with trigonometric substitution, a little bit more based on what we did from last stream. I did end up just, those of you who are watching on YouTube, you'll notice there's a gap, at least probably. Yeah, I neatly eliminated last week's stream because I was completely exhausted, and I did not end up getting a nice little nap at some point during the day or at night or anything else, and I was not terribly lucid. So anybody who was here can attest to that. If you're really desperate to see it and it's within 90 days or so, it'll be on Twitch. I won't delete it there. It is called Let This Be a PSA, Don't Stream While Exhausted. So if anybody's really desperate to see that, you can go check that out on Twitch. That will be a Twitch exclusive. And if you are a streamer yourself, hold that up as an example to yourself. Don't do what I did. If you need to, literally take a nap and come in later. That is not what I did today. Today was just, I was doing other stuff that was completely, totally important. Not at all surfing the web. Okay, so trigonometric substitution. We're going to look at what we were talking about last time. So the big idea here is that we've got some sort of integration that's going on. We've got just even 1 dx divided by the square root of 4 minus x squared, or something that looks remotely like this. The point is really that this stuff in here this is either going to be a Pythagorean difference or sum of squares. So if it looks like it's Pythagorean, hey, guess what? It's probably Pythagorean. What we're going to want to do with this is we're going to want to say, let's draw a picture to take a look at what we've got. So here we've got 4 minus x squared. This looks like, if it were a Pythagorean context, we have the hypotenuse, which is 2 squared, which gets us 4. And we have one of the legs. It doesn't much matter which one it is. You can decide for yourself which one you would like it to be. But usually we recommend doing integrals of either sine, secant, or tangent, because if you do cosine, cosecant, or cotangent, then you're going to have to worry about a negative. It's not like it matters, but it might be a little more helpful for you to think about that ahead of time and think like, which one is going to be helpful for me to actually have? So, in this case, if we just say, let's just have it be the opposite side here, x will get us the x squared on the inside of the Pythagorean difference, which then means that the third side here is the square root of 4 minus x squared. Okay. The main thing to keep in mind is that this is not a u-substitution. Where u is equal to 4 minus x squared. Because du is equal to negative 2x dx which is currently unattainable.
I thought I had it figured out.
Right, so we will not end up with a u substitution with u being 4 minus x squared, because there's no spare x on the outside. The negative 2 is not a problem, the dx is already there, but again, the x is not there, so that's where the problem lies here with a simple u substitution from, previous unit, basically. A little bit, it was talked a little bit in Calc 1. This is starting to get into Calculus 2. In most places in the United States, that's what it's going to be, right? Calc 2, Calculus BC, I think, are the two super units which are covered by this material. So here, if we look at this again, what we seem to have is, if we have theta, our angle that is on the in the standard position for a unit circle triangle, then what we've got here is the sine of theta is equal to x over 2, which is the easiest way to express all of this. We can then let this be x equals 2 sine theta, and dx, if we do calculus on this, is going to be 2 cosine theta d theta. So we have a substitution that this is going to work with our original problem here. So what we can do is replace all of the x's and dx's and everything like that. So we go through and we say we've got 1 over square root of 4 minus parentheses 2 sine theta squared times 2 cosine theta d theta. Okay, there are multiple ways to do this. So you can decide that we want the sine of theta to be equal to x over 2. And so therefore x is going to be 2 sine theta, dx is going to be 2 cosine theta, d theta. You could also say, we're just going to make dx equal to cosine theta d theta, and then therefore x would be sine of theta, and then we'd need to alter some stuff with multiplying some constants around. That's also possible. At the moment, I wouldn't press your luck. Right? If you're not familiar with this, if you haven't been doing it for a long time, I would recommend essentially playing by the book here. So we get our 2 cosine theta d theta, can multiply to the top, divided by, here at the bottom we get the square root of 4 minus 2 sine theta all squared is going to be 4 sine squared theta. Which is then going to get us to cosine theta d theta over square root of 4 can be pulled out as a factor. And then 1 minus sine squared theta is what's left over in the denominator. Integral of 2 cosine theta d theta all over. Here we get the square root of 4, which is 2, so these can divide out very nicely, times the square root of 1 minus sine squared theta is cosine squared theta. We now have the integral of cosine of theta d theta divided by the square root of cosine squared theta normally is going to be the absolute value of the cosine of theta. There are some arguments to be made here. Right? Since we already had a cosine squared on the inside, then we want to capture both the positive and the negative values that were in the cosine of theta. So that is going to be restored through this square rooting of a square. Unlike when we just do this with x squared, right? Square root of x squared, we need the absolute value. Here, the cosine of theta has both those positive and negative values just naturally. And here, we're going to divide out our cosine of theta in both places. We now have the integral of d theta, which is theta. And since this is theta, we also need a plus c for a constant value. It's not going to matter which coordinate systems we're using for this. It's all going to end up being the same. Then, theta cannot be left here. So we're going to have to go back up to this layer and say, we have the sine of theta is equal to x over 2. So therefore, if we take sine inverse on both sides, theta is equal to, right, theta is equal to the inverse sine, or the arc sine, of x over 2. Plus c. Alrighty. So that is going to be the solution for the family of solutions for the original integral up top here, where we had integral of 1 over the square root of 4 minus x squared dx. And as always, if anybody has any questions, Feel free to ask them. I will attempt to get to any other problems that are submitted, within a reasonable amount of time. Okay. I also have one that was from OpenStax. Okay, so evaluate the given integral in two different ways using u equals 1 minus x squared and also trig substitution. Alright, so first way to do it, again, u is equal to 1 minus x squared. This means that we have here du is equal to negative 2x dx, just as we did before. This is going to end up eventually being the same substitution, that we're going to have x is equal to 2 sine of theta. But in the meantime, so we have a couple of options.
So you can take amazing photos and share them on EE, because the most powerful iPhone
Okay.
yet deserves
If we substitute in u for the inside here, that means we just get the square root of u, and then x cubed becomes something rather interesting. So we need negative 2x dx in order to do this u substitution. We have a spare u in here, or a spare x in here. So we can make this, can't do that here, sorry, x squared times x. We also need a negative 2 to be inside of the integral, and then we need to balance it by multiplying by a negative 1/2 in order to just make that a form of 1, and we can kick this to the outside. So that's going to be a negative 1/2. This x squared, this part here is going to be our dx, du. Okay, so we have a du now. And then we have this x squared that we need to deal with. Well, we've got an x squared here. So if we shift stuff around a little bit, this says that x squared is going to be equal to 1 minus u. It may not look super cleaner at the moment, but it is actually a lot better. So we have this negative 1/2 sitting out front, an integral of the square root of u minus u root u du. And if we translate those into fractional exponents, this is going to be u to the 1/2 minus u to the 3/2 du. And if we remember how power rule works, right, we take the integral, the new exponent is going to be divided, because in order to get the current exponent, our integrated exponent would then be differentiated and it would come down to the front. So the other way to do this would be to say, okay, we need a 3/2, so now we also are going to have a 2/3 as a form of 1 in order to balance this out. New exponent, sorry, not a 3/2, 5/2, and a 2/5. Right, for the 1/2, we would also need a 3/2 by a 2/3. So that's where that one's going to come in. So here we get a -1/2 times the quantity. So here we're now getting a 3/2 u to the 1/2 du has an integral of, that 2/3 is still out there, u to the 3/2. And again, plus c, but we could just do that at the end. Minus u to the 5/2 times two-fifths. Okay, and then again, plus c. Just tacked onto the end because we don't need it anywhere in particular. All of the individual c's that come from each of the individual terms of u, we're going to get combined. They can get multiplied by -1/2. None of that stuff matters. It's still just an arbitrary added constant on the end. I mean, it matters, but we don't have to do it. Alright, so here we multiply by -1/2. We multiply -1/2 by 2/3. We get a -1/3 u to the 3/2, and then plus -1/2 times -2/5 gets us a positive 1/5 u to the 5/2 plus c. Oop, wait a minute, we're not done. So now we have to reassert our x's. So u is equal to, this is -1/3 times 1 minus x squared to the 3/2 plus 1/5 1 minus x squared to the 5/2 plus c. Okay. Secondly, how do we do this with trig sub? Okay, so the first way, or the first step to it, is draw on our diagram. This is our theta. And again, same as we had before, only this time our constant is just 1. So that's a 1 on the hypotenuse. And x on the leg. Let's just experiment and see what happens if we go the other way. So now x is on the adjacent side rather than the opposite side. It's not going to change much, but you know. Okay, and then square root of 1 minus x squared is going to be our other leg. So in this particular case, again, the cosine of theta is equal to x. X over 1 if you want to get picky. Doesn't really matter. And therefore, dx is equal to the negative sine of theta d theta. Therefore, we're going to get a cosine cubed of theta times the square root of 1 minus cosine squared theta. Phobos! How's it going? Good evening, welcome back on in. Is this one of those GRE math subject test problems? Technically, this one's too long for GRE. This particular question is from OpenStax because I wanted a harder type problem to get us back into the swing of things and prove that I'm not falling asleep this time. I was not in good shape last week and I should not have streamed, but I was like, obligation. No obligations, people. Don't do it. Alright, negative sine theta d theta. Okay. I think this is one of those famous trigonometric those wild trigonometric substitution ones that are going to have both cosines and sines with powers, and you have to reduce one of them, reduce the power of one of them. No, hang on. Nope, not this one. This one we're going to have to transfer all of them into the other one. So, you'll see what I mean in a minute if you're not aware already of what that is. Our 1 minus cosine squared theta is going to become sine squared theta on the inside of the square root.
What would you do? We'd go back to Hong Kong, to where we honeymooned.
And also, well, you know what? Let's do an intermediate step just to let everybody see the point. So here, this is going to be the square root of sine squared of theta. And this is we'll just throw the negative out front, and sine of theta d theta. Alright, this is a negative integral of cosine cubed theta times, this is just going to be the sine of theta to the first power, times another sine of theta, so that's sine squared theta, times d theta. Okay. This is where the interesting stuff happens. So, when we're sitting here, at this point, cosine to the third and sine to the second, we don't have a very convenient u du to be able to use here. You know, there's nothing that's immediately jumping out and saying, we should use this. But we can trade out pairs or sine squareds or cosine squareds for 1 minus that amount squared of the other one. So here, what we've got now is if we transfer all of the sines over to cosines, we're going to have odd numbers, odd powers of cosine functions. Well, that doesn't quite work, does it? Because then we don't have a u and a du. Again, if our u is a sine, then our du has to have cosines in it. And if our u is cosines, then our du has to have sines in it. So we do need both. However, we only need one of one type. And all the rest can be the other type. So if you notice, again, transferring sines into cosines is going to eliminate all the sines. So that's not really helping. However, if we transfer two of the cosines into sines, then we're going to have one left over. And that can be our du. So here we get a negative integral of cosine theta times, this is the cosine squared times sine squared of theta, d theta, negative integral. This is now going to become, again, we're going to kick this all the way over to the other side. We're going to translate this over. We're going to make this a 1 minus sine squared theta times sine squared theta times cosine theta d theta. Okay, now we get a sine squared theta minus sine to the fourth theta times cosine theta d theta. Okay, so now we've got it. If we let u be equal to sine of theta, then du is going to be equal to cosine of theta d theta. Oh, would you look at that? This one worked out very nicely. So here we do a negative integral of, this is going to be u squared minus u to the fourth times du. So, negative integral, the u to the square, to the second power is going to end up being 1/3 u cubed minus u to the fourth, again, is going to become 1/5 u to the fifth. I need to remove something. Right, and then we've got that negative out front, and then plus c. Okay. So then, this means from here, again, our c could have been any sort of arbitrary constant. We then have the negative sign that's out front. We've got constants on each of these things. They all multiply together. It doesn't matter. It's all just an arbitrary constant waiting for us at the end. We haven't plugged anything in, and that's going to be important. As we'll see later, potentially, if there is stuff that you plug in, then you have to be careful about when you plug it in and how you evaluate it. Alright, so this is a negative 1/3. U is equal to sine of theta. And here we're going to get a minus negative as a plus 1/5. Boo. Sine to the third. Come on now. Sine of theta to the fifth, all plus c. Okay, but now let's go back up top again. Sine of theta. Well, that was related to dx. So actually, let's go back up here and look at our triangle. We know what the sine of theta is going to be. It's that square root of 1 minus x squared. So here, this is a negative 1/3, parentheses, square root of 1 minus x squared over 1, but we don't need to worry about that, cubed, plus 1/5, square root of 1 minus x squared, all raised to the fifth power, plus c. Those square roots can be used as a half exponent as well. So a negative 1/3 times 1 minus x squared raised to the 3/2 power, plus 1/5, parentheses, 1 minus x squared raised to the 5/2 power, plus c. So what we got there? A. Right, so those are identical. We got the exact same thing in both cases. Good. Had to make sure. This route did take a little bit longer. However, it did require 2 substitutions. However, it does allow us a few more ins on this problem in order to say, you know, find where your strengths are in the overall problem. Allows multiple chances to corroborate. It also does some stuff like this, which I wouldn't probably want people to like really focus on a lot, but that does also cover it rather nicely for something we might do on the GRE. So, for example, you could have something that was to the effect of take the integral of cosine to the 7th theta times sine to the 8th theta d theta. How do you do this? Again, this one's actually pretty easy. We take a cosine of theta, we multiply by the cosine to the 6th of theta by sine to the 8th of theta d theta. Right, cosine to the 6th is going to be 1 minus sine squared theta. To the 3rd. Oi. Right, cosine squared theta parentheses cubed. Should probably put that in there somewhere. Times the sine to the 8th power theta. And then cosine theta d theta. Right. So now this would require an expansion, which is 1 minus sine squared theta plus 3 sine squared theta plus 3 sine to the 4th theta minus 1 sine to the 6th theta parentheses all that times sine to the 8th of theta, oops, times cosine theta d theta. So we end up with this raised to the 8th power getting multiplied to all these bits here. All of those individual terms again become a u-substitution if we feel like it, and then that allows us to build out all the bits here. Okay. Great. Next up is method partial fractions. I do want to say one more thing about trig substitution, and again, this was kind of, I talked about it briefly last time, and I brought it up a little bit this time. It's easiest, typically, if we use sine, secant, and tangent. So figure out what pattern these look like. Again, they're going to look like a Pythagorean pattern, either a sum or difference of squares, in which case, realistically, right, that's pretty much exclusively going to be that the sum of squares means that you have the hypotenuse is the square root, and so your two legs are going to be given to you. In the problem itself, or in the square root, and so just fill in the two legs. That's going to give you a tangent. And you can choose which one's which. So, like, make the opposite one your x. Right? Try to make it as easy as possible for yourself. That being said, right, you could have two different ways that a square root could be manifested here. One is that you could have something like 4 minus x squared, just like we did from before, or you could have something that is an x squared minus 4. And this is a different problem. Right? When we look at this, now this is saying, okay, this is the difference between the hypotenuse. The hypotenuse is now x. And one of the legs, which again in this case doesn't really matter, but if you want to make it typically easier, use it as your secant. Right, x squared minus 4. So here the secant of theta is equal to x over 2. Just out of curiosity, right? What does this do? If we did this as 1 and dx, ooh. Oh no. This would be a 2 secant theta tangent theta would be equal to dx. Draggy! Good evening and welcome. Dost thou in hoist? Just before break, too. Awesome. Good times. So, we're usually hoisting the 20 pound weights here, just doing some curls, and then keeping the rest of us just active a little bit. Some serious scribbles. Yep, so we're working on GRE, the Graduate Record Exam. In this case, it is calculus. It basically runs everything from some fairly easy pre-calculus type stuff all the way through topology, which I have never actually taken. So by the time we actually get that deep into the courses, I will find it rather interesting because I will be learning the material, not just having some fun with it. I have for the last 15 years, give or take, minus the last 1 year, 1.5 years, goodness. Okay, that's good enough for one. Been working at a community college in America, and we've been living for the last 1.5 years here in the UK, up in Yorkshire. So, took it in 2003? Yeah, mine's 2002. Well, okay. The book I have is 2002. My spouse and I took it in 2004 at the beginning of our senior year. It was right about now, actually, in 2004. So, it's been a while. Our GRE is now able to drink in the United States. All right, and we reduced to 15. Anybody who doesn't know, Draggy hangs out in Psyche's chat with me and a whole bunch of other people. So, apart from the last year and a half where I've been pretty much exclusively teaching on Twitch, I taught professionally for 15 years. And then before that, I was doing public schools, and I wasn't very good at it, quite frankly, for a year and a quarter. The quarter was at the beginning. So, yeah, we've been doing it a while. We have a number of friends here on Twitch who do all sorts of cool stuff, so looking for a career shift. Don't know if you can teach math. Well, that was one of the things that I did in the community college scene. Was I worked on the hiring committees, and that was actually other duties as assigned, not like, you know, not like I was part of HR or anything. Thank you for the workout. And there were people who, like, I mean, for the community colleges, they had no experience. They were just coming from industry or whatever. And it took a little bit of time for some of the people to transition just because they didn't quite know what was going on. But for the most part, a number of them were some of our best teachers just because they could relate a little bit better to the students compared to all of us ivory tower types who love the mathematics just for the mathematics. Business analyst for 2 years, experience running a business for around 10. Nice. Home renovations and reconstruction. Nice. So yeah, I'm very much just an academic, in love with the work itself. It is true, it is that sappy, but nonetheless, we have a good time with it. Complex arithmetic. Yeah. So the way that I taught, typically, at the beginning especially, but as the career went on, it evolved a little bit. Was basically I would, this is even pretty close to the end of my career there. I would do a lot of like, here, let's ask a question. Now let's show you like what reasonably could be the next couple of steps. What do you think in order to get this idea across, whatever it might be. In this case, right? Okay, let's say that I would have started from basic principles, right? So we would have said from this, like, what do you see here? Oh, look at that. It sort of looks like a Pythagorean, a right triangle stuff. Okay, let's build a right triangle. Now, which sides would this be if these were in a Pythagorean theorem? Okay, that one would be the hypotenuse. What's its size? That's x. What about this one? That's 2. Which leg? I don't really care which leg. Okay, let's just put it on this one. Why would we put it here and not there? That's because this is a secant. The derivative's easier. Instead of being a negative cosecant cotangent, it's going to be a positive secant tangent. Okay, cool. Yes. I'm also working a little bit, and I haven't really been working at it for basically over a year. But I want to start like cataloging all of the Common Core type stuff that the United States had been shifting to, and start talking about why these things are actually important, because a lot of people just didn't see it. They didn't know why anybody would be explaining things this particular way. Why not just do it the same way we learned it? And my response to that, generally speaking, is all the ways that we learned how to do stuff were just to get things done. They were not to understand anything. And a lot of the processes that we learned, a lot of the skills that we developed, are essentially intellectual dead ends. Which, like, if you're not doing your actual job in a scientific field, yeah, sure, who cares? Whatever. It's just doing a calculation, getting it done. You'd be better off, honestly, you'd be better off with one of these things. Algebra gives you a false sense of security. Yeah. Quarterly exams across the year. Started geometry. Yeah. Well, that's also another thing, is I want to, like, actually understand the British system, because I don't. I understand that it's more or less like, here's this year's worth of difficulty. Like, here's the concepts that we're going to teach, and here's the ideas to this level of difficulty. These are the problems we're going to solve, rather than, like, here are some objectives we need to make. Or the objectives are more problem-based rather than skills objective-based. So. Knuckle busters for the last quarter, yeah.
Travel far from where you are. Flying from Leeds Bradford Airport via Amsterdam with KLM Royal Dutch Airlines. Visit klm.co.uk.
And no trig on the 9th grade, yeah. Right, so with calculus, we end up here doing this one. Yeah, you hit it with theory. Yeah, okay. Fair. We get to this point, and we say, okay, if we want to, like, play around to rearrange this stuff. Yeah, it does get a lot of people off balance, and then honestly, a lot of people don't ever get it back. If you catch some of my VODs either here or on YouTube, if you're at all interested in remembering some of this stuff or having a slightly different approach to it, our math content at nsimplexpachinko6542 on YouTube is like, I have multiple times where I start trig, like, at the beginning, and start with a unit circle. This is how we approach all of it. And that's, you know, me after 15 years of learning my craft, of trying to teach something some way, and then students keep asking questions about it, so it refines my approach to it. And, you know, I grant you that's not exactly the approach that I would have used had I been in the classroom. That actually is, we're doing it on Monday nights, talking about the new approach that I would be using to this day, which is Building Thinking Classrooms by Peter Liljedahl. This is, like I said, a bit different of an approach. It's more or less like how to get students to work in groups such that they're actually doing the work and thinking about the stuff themselves, instead of always just being the person at the front of the room who has all the knowledge that is emptying things out into their heads because we know that that doesn't work. Get more retention if you start with algebra. Yeah. I mean, my parents did it right, quite honestly. They were like, you know, let's just do some simple problems in the car. And they would just talk with me about, like, you know, what's 3 times 2? What's this times that? What's this plus that? What's this times that plus that? And so we'd start building this out further and further, and then they'd say, okay, so like what plus 7 is 3? And I'm like, oh, well, I mean, or other way, what plus 3 is 7? Okay, and we'd reason it out, and then eventually they were like, so if you just replace it with like X or A or something like that, you can do that. And I was like, okay, and then that just became our language. And like my dad had differential equations, so he was, you know, about associate's level mathematics. My mom was she was a nurse. She went the statistics route, where she didn't have to take that much math intentionally. But nonetheless, the both of them like absolutely hooked me in to math and algebra at age 8. Like, that was what we were doing in the car when we were just chatting. And it's kind of wild looking back on it, just thinking about how much they ended up forming that for me, forming the framework of like where I started. That was also really big because we used to watch Square One TV, which was a PBS show back in the States in the 80s and 90s. And Square One had like just so much math content in it. Simple arithmetic. They would do music videos. They would do, you know, all these little sort of cutesy things. Variety show for the first 15 minutes, and then the last 15 minutes was devoted to MathNet, which was a riff on the old Dragnet TV show. And every problem, they solve it with mathematics. And it's all 5 days during the week. Monday through Thursday are the setup, and then Friday's the payoff. So, it's good times. In India, you have the syllabus dealt to you at the start of the year, so you know what... Yeah. Yep. Even give you the exam dates ahead of time. Yep. Us too, with the community college. Always good at maths. 70 aggregate, yeah. Pushed it to 94. Nice. Awesome. Yeah. We'll come back to this. I'm gonna run downstairs, grab some stuff. We're about to hit ad break, so anybody who's interested, we'll also do a quick martial arts break. When I come back, we'll do I don't know, probably Tang Soo Do, karate. So, see you in 3. Thanks so much for coming. Awesome to see you, Draggy. And yeah, we'll be right back. Alright, welcome back. So, doing some Tai Chi warm-up like we usually do here. This is just to get the joints, synovial fluid, and all that good stuff moving a little bit. Basically, you just let your arms hang, and then if you put your legs apart, you could just get your arms moving like a swing. Don't put any energy into it at the shoulders, just let them go where they're going to go. And try not to let them go clunk like you're, you know, a kid trying to do a flip over on the swing. Yanking too hard on your shoulders and muscles and things like that is not good for them. So, especially when you're over 40. When did that happen? God. 3 years ago. Yeah, I know. So anyway, we do something like this just to warm up a bit, and then we also stand about, shoulders width apart, maybe a little bit more, and then do kind of a windmill sort of thing. But instead of just doing a windmill sort of thing, you also add a little bounce to it when your front hand is going down from across your body to kind of like whip outward. Again, don't put too much energy into it. At the shoulders, there's none. But what I'm doing is that I'm just bouncing a little bit in the knees, spinning a little bit, and it's just causing it to fly as it will. Body mechanics are pretty awesome. So we learned all this stuff in Tai Chi. It's applicable to just about everything. And let's actually... Alright, let's do this officially, I guess. Boop. Right. So from here... Stop turning. Stop turning. How about that? No, you still don't like that? Alright. Somewhere in there. So, I'm going to do my second black belt form, which is called Basai Dai. It is a bit long, but worthwhile. So this is from Tang-Soo-Do Karate, which was made popular in the United States by Chuck Norris. You might have heard of him. Yes, that guy. My particular school was not affiliated whatsoever. We had a guy by the name of Dale Tompkins, who like kind of created the Mid-Atlantic region version of Tang-Soo-Do Karate, which involved a lot of joint locks and other cool stuff from Jiu-Jitsu, a lot of kicks, punches, etc. from Taekwondo, and also some of the stuff from its parent martial art called Mudokwan. So there was like a big mixture of stuff. So Basai Dai, typically start with, as usual, Junbi. And then we start with a tension up to the front. And then we turn to the side, let our balance come off a little bit, and we step with a reinforced block. And then from here, we do a step back the way we came with a outside in? No, inside out block. And then immediately follow up with the other side. Then we do a D to draw, and it's going to be a double uppercut. So we come this way, do a double uppercut, and then we go back into... It's a down block and an up block. I don't even know how to describe what I'm doing with my feet. So it's like you're trying to parry something with your feet, or trying to prevent it from kicking you, and make sure I'm not going to hit anything. So from here, we go back like this, and I'm trying to come back up and put my foot back in the crook of my own knee, or on the back of my calf. And we do a up block and down block at the same time. Then we do a down block in the right direction, like that. And then we have to come back to the center in a Kima stance. Tension across. And then here we do a chop, punch, uppercut, back fist. You know what? Can't see this terribly well. Hi, Zach. How's it going? Let me bump that out to that one. Now you can see every mistake that I make. Right, so we had a double uppercut. Hello, Zach, and hello, everybody. My name is Obi-Wan Pez. This is N Simplex Pachinko, and right now we're doing karate. So we do a double uppercut, and then come back, and we do a up block, down block, and reinforce something on the back of our... I don't know what this is supposed to be. Pen!
I have a pen. I have an apple.
Oh, is it here? It might be an inside-out block.
Apple pen.
Hello there.
It's also me! Right, now we come across, and then we do a, like I said, from a Kima stance way down here, we do a chop, a punch, and then a back fist. All with the same, or with like going 1, 2, 3. And then we have to do the opposite, so we go with, from here, chop with the right hand, punch with the left, and then back fist with the left. Thank you so much for the follow. We're just doing a quick redeem for basically keeping myself active and making sure that I don't forget all of my karate in the next 2 years or so. And then we go to a Fugal Sudo. Most of the weight is on the back foot. The rear foot is pointed 45 degrees back, give or take. The front foot is pointed straight out, and then our hands are coming out. This one's protecting the sternum and our solar plexus, because you do not want to get hit here. It's awful. And then the front one is coming out and blocking something. So that's 1, 2, and 3. On the third one, we parry down, coming back off of that, and reinforce here. We're in this really awkward stance, and then we are grabbing something here, bringing it to our hip, all while trying to do a side kick. All right, hang on. Right, I was foreseeing this thing just flying off my head. It's all good. Hey everybody, how you doing? Okay, so we do side kick, and then we drop into a Fugal Sudo going backward. We do 1, and then here what we do is a double up block twice. Funnily enough, we do a rib cracker, where we basically come down and do a double fist strike right about where the floating ribs are. and then hop forward and do a punch. Okay, from here, this is the second half of the form. I told you it was a long one. We're going to do a groin strike back over to here. And then we come back up into a... It's a Kima stance again. So here, basically doing a groin strike, a grab and rip. Don't ask. And then we go the down block here. I think this is right. It's been a while. So we do a down block, and then we do a ridge hand back this way. We do a crescent kick into it, and a head smash on our elbow. And then, with the person that we've just knocked on the ground, we punch them twice. From here, almost done. And then I'll actually look and see what everybody's saying. We come and do a tension across, and then we do a double punch this way. So we're in this like kind of awkward chunkle stance. We do a double punch this way, step back up, come around no, that's wrong. Okay, we did that, come here, kick around this way. We do a crescent kick, followed by another double punch this way, pop around again, do another crescent kick, and a double punch this way, and then we have to get stuff out of the way, come around to a Kima, do two, basically you just let gravity do the work, take your back fist, bring it down onto the target on the ground, reverse, then, oops, I just opened the car, and then we do a Fugusido this way, and then we do a jump change. That was wrong. Here, jump change. There we go. And then we're back to tension. And chumpi. Can you? If anybody actually knows the Korean for that, you can feel free and comment. Yes, it is Math Man. I have been trying to get more of the Square One TV, MathNet, like sounds and stuff like that, but I for the longest time I have had issues with Audacity, and I just got it to work properly. So now I need to find the time to actually do it. Which, like, there's plenty of time, it's just a matter of, like, not having other things to do. Well, anyway. Hello, and if anybody somehow does not know me yet, my name is Obi-Wan Pez. This is N-Simplex Pachinko. We do mathy type stuff on Mondays and Wednesdays. And we do gamey type stuff on Sunday, Tuesday, Friday. So, currently, we're working on, on Mondays, we're working on Building Thinking Classrooms in Mathematics by Peter Liljedahl. We're doing a kind of review of what it is that this thing actually is. And we're also doing a commentary on, like, what have I found in implementing this particular method. Why does the theory support it? What studies have been done? Basically, the only studies that I have at the moment are the ones that are in the book that actually are like written into the appendix. There are more, and I need to look them up. So, like, go hunt down archive or whatever. I'm sure it's not difficult. In addition, on cheap viewers, really? We have the best viewers. You are a bot. Selling viewers, and time is 0004 BTC. No, BST. What is BT? Bitcoin. I have no idea where that came from. Okay. Anybody who knows me knows that that would not be a thing that I'm really into. Anyway. Thank you so much, everybody, for coming on in. And we are working on, currently, our Wednesday night project is to go over any mathematics that people would like to go over, filling in any time that is extra, i.e. the framework that we start with is cracking the GRE math test. This is the math subject test for the graduate record exam. Currently we're up to Calculus 2, or Calculus BC, or whatever else you want to call it. We just started on, or we're just finishing up Trigonometric substitution, and we'll be getting into partial fractions next. If anybody has any other questions about mathematics, about what, you know, philosophies or various other stuff like that is, you can ask anytime. I will always commentate on it. I may not always be 100% attentive if I am also playing a live game, like, you know, Elite Dangerous or something like that, where, you know, there is no pause. But I will always have an answer. Furthermore, tonight is hashtag not sponsored by Vault City chocolate dipped strawberries. Scottish strawberry preserves and chocolate infused sour. It's interesting. I was feeling in a harvest fruit sort of mood, so it's working out pretty well. So anyway, yes, we also take study breaks regularly. In addition to running the ads, we also do martial arts. So that was Tang Soo Do Karate. I have been a member of a particular organization in Maryland for roughly 17 years, on and off during COVID and when I was getting my master's. And now, because I don't live in Maryland anymore. But we are planning on going back eventually, and we'll see how it goes. Currently, I am also a student of Eskrima, which is a machete-based sword art. It uses typically sticks as analogs because, quite frankly, beginners with machetes is a terrible idea. We do, however, have the, I don't have them, but our instructor has the ABS plastic, I think, that are 3D printed or injection mold printed, injection molded, whatever, into the actual shapes of actual swords. So that's pretty cool. They're weighted improperly, but you know what? It's close enough. Really, what's important, though, is that they do have the whoosh sort of feeling, and when you get it wrong, it is very loud of a whoosh, and when you get it right, it is a very high-pitched. You barely hear anything, but you can hear, and I love it. And also I take from the same guy, Tai Chi. So we're working on Tai Chi Chuan, which is the more combative side of Tai Chi, which is very much not your grandmother in the park sort of Tai Chi. It's some really cool stuff. So we're also learning how to use the biomechanics of the Tai Chi in also doing our karate and doing our eskrima, and it is beautiful to fuse all those pieces together. So it has been a very interesting couple of years. When I go back to Maryland, I am going to pursue my black belt in Tangsa-do, and I think I will probably have a bit of a shorter road than I did before, despite, you know, having all those things. A little less than 2 years. So, in theory, August 27, we'll see how things are. And what the job market is looking like. If the UK is desperate for us to stay, they'll let us know. They probably won't be, but we'll see how things go. 30. All right, timer set. So, before we had everybody come on in, before we had ad break, we were working on some this thing. We were looking at some trigonometric substitution, and specifically we were looking at what would it be if, instead of having our x as one of our legs of the triangle, what happens if the x is the hypotenuse of the triangle? So, in theory, right, you could do what you want with it, but realistically, if we let that be a secant, then we can have x in the numerator, and it makes everything just that much easier. So, unfortunately, a bit, the denominator is a secant tangent. However, probably fortunately again, plugging some of this stuff in is probably yeah, okay. Wow, okay. Yeah, we're good. Yeah, plugging some of this stuff in the way we have it is going to work pretty nicely. So this is 2 secant theta as x, and 2 secant theta tangent theta is dx, d theta is dx. So make sure you leave yourself enough room to actually write the things you want. Okay, so now we can replace everything in that integral. The numerator, instead of being 1 times dx, is now just going to be all that stuff. So 2 secant theta tangent theta d theta The denominator is going to be the square root of, this is 2 secant theta parentheses squared minus 4, which is the square root of 4 times the quantity secant squared theta minus 1. Which, if we look at this in our standard Pythagorean triangle here, we had our sine of theta here, cosine of theta here, and 1. Or, if we look at it in terms of, if this is the so close. If we look at it in terms of our unit circle, then our tangent is going to be this distance here, which goes up to that point from the edge of the circle. Tangent is going to be that height. The secant is going to be the distance that is going outside the circle here. And this distance coming across and going to the edge of the circle is going to be 1. So 1 plus tangent squared theta is equal to secant squared theta. So therefore secant squared theta minus 1 is equal to tangent squared theta. Just in case you needed a little extra reminding on that one. So here we get 2 secant theta tangent theta d theta over, this is going to be the square root of 4, which again is 2, so it divides out from the top. Oops, sorry. And this is the square root of the tangent squared of theta. When we take the square root, we get a tangent of theta, and so that is going to divide out that. And so now we have the integral of secant theta d theta okay. Integral of a secant. I don't think that that's particularly nice. So let me go back a step. If instead we did this, how nasty is that going to be? It's just literally going back to the same thing. Okay. Yeah. Right. So we can't just reverse it and be like, oh, it's just going to be the... So if we involve ourselves with the opposite side at all, this is going to end up with some nasty stuff. Okay. No. There's something we can do with it. Oh, how do you get the integral of a secant? It has been a super long time since I did that. Okay, so this is the integral of 1 over cosine of theta d theta. Come on, integration methods, don't fail me now. So, what else can we do with this?
Over your skin, you can see it beat, intoxicating your energy. First time in so long, you felt the heat evaporating your binding.
So we can't do a u-substitution because the cosine would then need a sine as its du. Inspired substitution. Multiplication by 1. So I would like to have a sine. But if we have it both top and bottom. Oh. Wait. Ah. Yeah. So actually, was I right in what we were talking about before? No, not that. GCF's in the function derivative, right? So we want... Right, okay, thank you. Yep. So actually, right, what we had before was wait. Ha. Yeah. Can they both functions in the denominator? So I mean, if we do that, that's more awkward. Closer, yeah. Ugh. Need a different operator in the denominator. Yeah, thanks. Are we doing addition? Okay. So if we do plus tangent theta. I don't think I taught it this way before. It's kind of gross, but it's pretty awesome. Right, so if the denominator is secant theta plus tangent theta, then the derivatives of the secant are going to be secant tangent, and the derivative of the tangent is going to be secant squared. So all times d theta. Yeah. Commutative property, super important in mathematics. Thank you. So yeah, this is going to end up being secant theta plus tangent theta. This is now going to be, if we do this again, push it around the other way and distribute the secant in. Ugh, gross. Totally enough room. Right, then this is going to be, we let secant theta plus tangent theta be equal to u, and therefore secant theta tangent theta plus secant squared theta is going to be parentheses d theta equals du. Right, so this is now going to be du over u, which is nice and easy. That's just a natural log of the absolute value of u plus c. And then here we say that this is going to be the natural log of the absolute value of, and this is why we get that weird secant theta plus tangent theta inside the absolute value of a natural log. Like, where in the crap did that come from? It came from here. So if you were ever wondering. Okay, and this is going to be the natural log of the absolute value of the secant of theta is going to be x over 2 plus tangent of theta is the square root of x squared minus 4 over 2. Plus c. 1 plus sine of x all over cosine of x.
Some days it feels like your to-do list just won't quit.
of the inside of that.
Let Halfords take something off your plate. We're here when you need us.
Oh, yeah, right, yes. So cosine is the denominators. I don't find that any easier, really. I mean, maybe it is a little bit, but...
Book online at halfords.com or give your local Halfords garage a call and we'll sort it. So you can keep moving with confidence.
The other amusing part of this is that you all are going to be hearing all of the British advertisements that have nothing to do with you based on your region. Okay, so we see some of this fun stuff here. Again, if x ends up being our hypotenuse, then we end up with, you know, the much bigger, more awkward stuff here. As Zach said, it can be 1 plus sine of x all over cosine of x, and it makes it a little bit easier, maybe. But it's not too bad, all things considered. Right, and if you know your integral of secant, then it's less of a problem. But I wanted to make sure that we got it from first principles, just so that anybody, and not to mention I did not remember it. If anybody does want to see why something works, this is also a hallmark of the work that I do on this channel, is that I really want to make sure that we have it from first principles, from already known clear knowledge, and work from there. And again, thank you for the follows to the people who followed earlier. In addition, what we wanted to work on next was method of partial fractions. Okay, this is saying that if we do or have an integral that says 1 over x to the 4th minus x squared dx, then what we want to do is to be able to break this particular fraction up into multiple fractions and be able to do some sort of method on it that's going to work nicely. As it is right now, right, there are no ways to break this fraction up into nicely integrable fractions, or anything else for that matter. There's just no way to break this up nicely. So what we're going to do is we're going to say that we want to, first of all, factor this the best we can. So here we're going to take out x squared, and we're going to be left with x squared minus 1, which can also be factored. X squared into x plus 1, x minus 1 dx. Okay, now what we would like is for each of these fractions to be in sort of its lowest form. So what we would like is that there should be some number a over asterisk, give me a second. Now, you know what? Let's go the other way. So a over x plus 1, right? And a, just a regular constant divided by x plus 1, cannot be divided further. At least not nicely. If we had something like 2x minus 3 over x plus 1, we could actually divide that in. We did this in polynomial long division way back when. If we did 2x minus 3 divided by x plus 1, we would be able to say, oh, that's going to go in twice. We get 2x plus 2, and then when we subtract it, we have a remainder of -5, which has yet to be divided by x plus 1. So this is going to be the solution for that division problem, 2x minus 3 over x plus 1. So what we want to say is there should be no solution, no further quotient to be had. So a over x plus 1 does not allow us to make anything else. We cannot find any better quotient than this. So constant divided by linear. Cool. We're going to do the same. Plus b over x minus 1. Same deal. Plus, now we want x squared in the denominator. So what is the smallest object that we can put in the numerator such that x squared cannot be divided into it at all? Okay, that is not just going to be a constant this time. It's going to be a linear function. So cx plus d divided by x squared has no nice quotient to work on here. Again, if it were a quadratic divided by a quadratic, we could divide x squared out of the numerator. If it was just a constant, we could be missing the linear term. There could be a linear term, and we wouldn't have it. So here we want to make sure it's represented. So this is the polynomial, not polynomial. This is the split of the fraction above that we would like to exist. So the next question is it possible? In most cases, yes. You would, in fact, be able to break up any particular fraction you want into the sum of fractions that have the same denominator. So, for instance, right, if we did like 1 over 9 times, and I'm not going to use the exact factors that are there, but you know, we just want two other numbers. Let's say that they're prime. So 5, sure, and 7. You know what? Close enough. 1 over 9 and 5 and 7. So overall, that's going to be 35 by 9 is 315. Right, so here this is 1 over 315. Haven't been over at pens enough times and done QEDs, but mental math, right? Kind of important. And again, you'd be better off with one of these if you need some sort of calculation device. This is, by the way, a Japanese soroban. It has 4 in the ones column, or in the ones space, and 1 in the fives column. The Chinese abacus has usually 5 in the ones space and 2 in the fives space, so that you can trade over a little bit easier. In the Japanese soroban with the 4 and 1, you have to do a little bit of mental math here and there. But with the Chinese abacus, it's basically like you're just making change. Okay, so we're going to show that we can, in fact, make this as some sort of fraction. And again, we'll make this Okay, if this is 9, 5, and 7.
We'd go back to Hong Kong, to where we
Dim sum for breakfast? Ooh, sign me up.
Right, it could be a fraction.
We'll take a samba class and samba on down to to solve.
Travel far from where you are. Flying from Leeds Bradford
Okay,
Airport.
this is technically, right, x squared, 2x minus 1, and 2x plus 1. So, not exactly the same as the other one, but you know what, close enough. We would want this as some sort of linear combination of 3. And we would want both of these as constants. So right here we're saying there has to be some sort of numbers A, B, C, and D, which will, when added together in the appropriate fashion, end up getting us 1/315. We can actually do this if we want, but it's not like it's super important. Sure, why not? Right? If we say, let's multiply everything by 315, which is, again, 9 by 5 by 7, then the first term is going to have 3a plus b multiplied by the 5 and the 7, because the 9 is going to get divided up, plus c times the 9 and the 7, because the 5 is divided out, and d times the 9 and the 5, because the 7 is being divided out. This may not work entirely, but that's alright. We'll probably just have to lean on the other one. It's fine. Yeah, there's not enough information, really. 105A plus 35B plus 63C plus 45D. We'll come back to that. As I said, the issue here is really that we don't have enough information in order to make that work. But, right, can we do something ridiculous and just like add 2 of the numbers and then get the same as the other 2 numbers? So if that was 140, no, that's not enough. Nah, it's not just one of them. So anyway, it's going to be off by a bit. In this case, with all the variables, we're going to do the exact same thing. We're just going to tweak them a little bit and say, what I want is that 1 over x plus 1, x squared, x minus 1 should be equal to a over x plus 1 plus b over x minus 1 plus cx plus d over x squared. We should get the exact same answers for the integration as for this problem right here. Alright, multiply everything by that denominator. So x plus 1, x squared, x minus 1. We get a 1 on the left-hand side is equal to a times x squared times x minus 1 plus b times x squared times x plus 1, because the x minus 1 gets divided out, plus cx plus d multiplied by x plus 1, x minus 1, because our x squareds get divided out. Alright, 1 is equal to. This is going to be ax cubed minus ax squared plus. This is going to be bx cubed plus bx squared plus. Right. This is going to be less fun. Let's re-multiply this so that this is x squared minus 1 here, and then binomial multiply with cx plus d. We end up with cx cubed minus cx plus dx squared minus d. Okay, combine like terms. So a plus b plus c is going to all be an x cubed term plus negative a plus b plus d are all going to be x squared terms. Plus, okay, we could just do a minus on that one. It's going to be minus cx minus d. That's it. Now, the thing with this is that every individual term on the left and on the right need to have the same coefficients. So over here, this is a 0x cubed plus a 0x squared plus a 0x plus 1. So now we're going to equate. This is a plus b plus c is equal to 0 because those x cubed terms must have the same coefficients. All right, adds are going to hit, so we'll let those run, and then we'll be back here in 3 minutes. Thank you so much for coming. We'll be right here.
The night has come, it's cold and losing my control. Your light is gone, and lonely darkness fill my soul. I wish that you could save me from my isolation. It's way too complicated. Stop this conversation. Stop this conversation. We got no relation.
Alright, welcome back. So, if we're doing this by regular algebra, we've got a plus b plus c equals 0, negative a plus b plus d equals 0, negative c equals 0, and negative d equals 1. So clearly, d equals negative 1, c equals 0, so that clears that out from the first one. We just get a plus b equals 0. Second one, we've got negative a plus b minus 1 is 0. Shift the negative 1 to the other side. A plus b equals 0 and negative a plus b equals 1. So add them together as equations. We get a 0a plus 2b is equal to 1. Therefore, b is 1/2. And since a plus b equals 0, a equals negative b, which is negative 1/2. So now we've got a, b, c, and d for all of these things. Okay. Which means that our... This is negative 1 over 2 parentheses x plus 1. Right? A is x plus 1. B is a positive 1/2. So 1 over 2 parentheses x minus 1. Okay, plus, this is now our x squared in the denominator. Up top we had cx plus d, which is now just going to be 0x minus 1. So now it's a negative 1 over x squared. So this is now our actual integral. Now in the first case, we've got a negative 1/2 multiplied by, that's just our constant. X plus 1, we take the integral of it, we get the natural log of absolute value of x plus 1. Plus, we get a 1/2 that's multiplied out front, and again, 1 over x minus 1, we take the integral, that is a natural log of the absolute value of x minus 1. Okay, and then the last one, we've got a negative 1 over x squared. So when we take the integral of this, we have our current exponent is a negative 2. Our new exponent is going to be a negative 1. So we have to divide by negative 1 in order to get all that through, or we use negative dx as part of our u-substitution and all that good stuff. So this is going to be a plus 1 over x plus c. Okay. Now, these other two bits, because they're both natural logs, we can move around exponents. Because these are natural logs, the constants out front can be manipulated into place, or we could say, well, they're both a half natural log absolute value. The positive one is going to be x minus 1, that's going to be on top. And the negative 1 is going to be x plus 1, and that's on the bottom. Now, when we're looking at this, question is it any different? Flashbang out. Is this going to be any different? Nope, not linear. ln absolute value of x plus 1. Oh, stop. Minus natural log absolute value of x minus 1. Alright, it's going to look like this. Let's just make sure that this is correct. I'm going to leave off the half in both cases. I just want to double check that this is in fact what I need. It's x minus 1 is the positive, x plus 1 is the negative. Yeah, I went backwards. Boop. So, mirror reflection of the other one. Natural log, absolute value. And now what we do is we go with the fractional version of this, which is x minus 1 over x plus 1. Okay, so this is identical. We don't have to worry about some weird edge case. I just wanted to double check. Okay, and then this is plus 1 over x plus c. Alright, 1 over x plus natural log square root, which is the 1/2 out front, multiplied, is an exponent on the inside. X minus 1 over x plus 1. Plus c. Yep. That's what the book has as well. So here, again, we could bring in the 1/2 as an exponent. Right? This fraction must be positive in order to make this yep. This fraction must be positive in order to make the square root work. So we don't have to specifically address that it's an absolute value or what have you. Okay, plus 1 over x plus c. Sorry. Right. So let's grab another example from our OpenStax text. Actually, this is a good point here. Oh, right, linear algebra. In order to complete the linear algebra version of this, we can say that we're going to add together row 2 plus row 1 plus row 3 plus row 4. Put back into row 2. On top, we've got row 1 plus row 3. Put back into row 1. Negative row 3. Put back into row 3. And negative row 4 into row 4.
What would you do? We'd go back to Hong Kong, to where we honeymooned.
Okay, so that's going to be row 1 plus row 3 is going to get us 1, 1, 0, 0, 0. The sum of all 4 is going to get us a 0, a 2, a 0, and a 0. Gets us... Oh, the sum of all 4. Yep, gets us a 1. Negative row 3 is going to be 0, 0, nope. Positive 1, 0, composed with 0. Composed? No, it's not composed. 0, 0, 0, 1, negative 1. Okay. 1/2 row 2 put back into row 2. And then row 1 minus 1/2 row 2. Is going to get us a 1, a 0, a 0, a 0. And minus half row 2, so minus a half. 0, 1, 0, 0, 1/2, 0, 0, 1, 0, 0, and 0, 0, 0, 1, negative 1. So A is equal to negative a half, B is equal to a half, C is equal to 0, D is equal to negative 1. Right? Yes. Good. Got the same thing. That's important. Okay. This version here is called the row reduced echelon form, often known as RREF. And that is when we have the identity matrix on the left-hand side augmented, that was the word I forgot, augmented with the constants that we get. This actually comes from a product of matrices that will allow you to show a system of equations as like a series of matrices rather than doing them as individual equations. So in linear algebra, this is saying that we had 1, 1, 1, 0, negative 1, 1, 0, 1, 0, 0, negative 1, 0, 0, 0, 0, negative 1, multiplied by, this is our A, B, C, and D vector matrix. Is equal to, we started out with 0, 0, 0, 1, the constant matrix. Right, So the number that's on the right-hand side, left-hand side of the equation in this case, right-hand side of the equation in the augmented stuff. So this whole system of equations is abbreviated into this form. We do some math with each of the rows using row operations, and that's what we end up getting. Right. If anybody has any questions, let me know. Here. Integral of x squared plus 3x plus 1 divided by x squared minus 4 dx. Alright, there is an interesting problem with this one. Namely, that if we try to go x squared plus 3x plus 1 all over x squared minus 4 is equal to, we would get here that this splits into x plus 2x minus 2. So a over x plus 2 plus b over x plus 2. So note the x squared term can still be divided by x squared minus 4. And if we were to do that, right, we would end up with long division. So in this case, through 1 divided by 2. It's going to get us, that's not what I want. Oh, come on. One, 2, 5, 7, 11. So we're going to have x plus 5 plus 11, which has yet to be divided by x minus 2. And then all of this stuff still needs to be divided by x plus 2. And here we could see that x plus 5 is really close to being divided by x plus 2. I mean, if we wanted to, we could make this x plus 2 plus 3 plus 11 over x minus 2 all over x plus 2. Okay, the x plus 2 here would divide out. We just get 1 plus 3 over x plus 2 plus 11 over both. So this creates a problem. Because now we have this quadratic function in the denominator, and we don't have that up top. So, oh, geez. X minus 2. Good job, Obi. Come on now. Okay. So here, what we need to do is first divide. Alright, so x squared plus 3x plus 1 divided by x squared minus 4. Right, this is 1, x squared minus 4, and then we're subtracting, so this is going to be a 3x nope, we're adding, so that's going to be a plus 5. And now we wouldn't be able to divide it, so this is going to be a 1 plus a 3x plus 5 over x squared minus 4. So now what we've got is an integral of 1 plus 3x plus 5 over x squared minus 4.
Some days it feels like your to-do list just won't
dx.
quit. When life gets hectic,
Right, so then we can just do this portion. So now we've got 3x plus 5 over x squared. Well, hang on. Do this as x plus 2x minus 2 is going to be equal to. Now we're going to do just 1a over x plus 2 plus b over x minus 2. Okay, if we multiply everything by x plus 2x minus 2, we end up with 3x plus 5 is equal to a times the one that's not there, x minus 2, plus b times the one that's not there, x plus 2. And now if we look at this, we got 3x, nope, plus 5 is equal to ax minus 2a plus bx plus 2b. Okay, and then again, combine like terms, so 3x plus 5 is equal to a plus b parentheses x plus parentheses negative 2a plus 2b. So a plus b is equal to 3. Negative 2a plus 2b is equal to 5. So 1, 1, augment 3. And negative 2, 2, augment 5. Alright, so this could be row 1, no, row 2 plus 2 row 1. Put back into row 2. And then weight. This is going to be a 1, 1, 3. This is going to be a 0, 4, and 11. Ew. 3, 0, 1, 11/4. Okay, row 1 minus row 2. Put back in row 1. Get a 1, a 0. And then we're subtracting row 2 from row 1. So we're subtracting 11/4 from 12/4 is going to be 1/4. That's not on this row, it's the one above. This one's still 11/4. Alright, so 1, 0, 1/4, and 0, 1, 11/4, which means that we have our numbers. A is going to be equal to 1/4, B is going to be equal to 11/4. And then we can solve the integral above. So this is the integral of 1 plus 1 over 4 parentheses x plus 2, I think. Yeah. Plus 11 over 4 parentheses x minus 2. That should be it for that one. Dx. This one's going to be x. This one's going to be 1/4 the natural log of the absolute value of x plus 2. This one is going to be an 11/4 natural log absolute value x minus 2. Dx. This is a 1/2 x squared. Boo. Plus 1/4 natural log. Again, let's combine these. So this is going to be a natural log absolute value. Nope, 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 nope. That wasn't it at all. This is a 1/4 out front. Then natural log absolute value x plus 2. Then multiply by 11 absolute value of, no, not natural log, of x minus 2. Right, so that... Ugh, man, I just did double integrals. Cool. Plus C. Not dx. Okay. And that's going to be it. Obviously, we could mix it around a little bit, change it slightly. x plus natural log of 11 times the absolute value of x plus 2x minus 2. And then raise to the 1/4 power. Take the 4th root, whatever we feel like. That 11 needs to be part of it, though. And then plus c. So something like that. X plus 11/4 natural log x minus 2, 1/4 natural log x plus 2 plus c. Yep. Cool. Right. So now let's go over and see Dr. Gold, who just got on about 20 minutes ago. He also does math and science type stuff. He's got a non-profit that he runs, Actual Education, I think. And we will head on over there. Everybody get your questions ready just in case. And we will see you next time. I will be back on Friday, barring anything weird. And we'll play some Against the Storm. Friday nights are our For the Long game. So we typically do some sort of long game, long play that goes in there. Sunday we'll be back again for Satisfactory. Currently we're working on optimization and it's going to take forever. Next Monday we'll be doing Peter Liljedahl's book, Building Thinking Classrooms. Tuesday we will do more Nine Souls and start exploring more of the other areas that are around us. Try to find, there's got to be a double jump or something in there too. So we'll see if that's in there. And next Wednesday we'll be back for more this stuff. Cracking the GRE. In the meantime, I hope you all have a great rest of your week. Have a great start to your weekend. And we'll see you then. We'll also probably be around on all of the other channels with Zach and Dawn and PhoboStream and anybody else who's out there. Thank you so much, everybody, for coming. My name's Obi-Wan Pez. This is N Simplex Pachinko, and we'll catch you next time. Thanks.